So here we start to take our journey from just learning what the elements are on the periodic table, which we've already done, and we're taking our journey into understanding chemical reactions. The first step in that is to understand what an ion is, and that is the topic of this lesson. So I'll give it to you in words, I'll write some things down, and we'll make it concrete by the end of the lesson. Basically, all of the elements on the periodic table, they're what we call neutral. So the atoms are neutral. They have an equal number of positive protons in the nucleus and an equal number of electrons that are surrounding. So because you have equal number of positive and negative electrons, then if you look from a distance at the atom, then it looks like it has a net charge of 0. Because positive plus negative, if you have the same amount of them, is equal to 0. All right? But if you have an imbalance, like if I take an electron away, then I no longer have a balanced number of protons and neutrons, and then you would have an ion, okay? Or if I add an extra electron to a neutral atom, I'm going to have an imbalance in the protons and the electrons, which again will give me an ion. So this lesson is all about what are ions, how to figure out the charge on an ion, and understand how ions are basically formed. And as we go forward, that's going to allow us to predict how things are going to bond together, because the ions are very important in understanding how, for instance, sodium comes into contact with chlorine, making sodium chloride, right? Because the ions are critical in that happening, essentially. So let's jump in and let's just kind of like write down what I just mentioned. So an atom has an equal number of positive electrons and positive protons and negative electrons, and because of that, it's neutral. Now, when I say it's neutral, I mean if you zoom up on top of the atom and put your sensor or your eyeball inside of the atom, of course you can see the individual charges. I'm talking about from a distance. You're going to see equal number of positive and negative, and you won't see any from a distance any distinction or any distance between them, and so it'll just look like a neutral object. And that's what's around you all the time. That's everything I'm touching is a neutral object, essentially. So let's take a concrete example of that. Let's talk about, I could pick any element on the periodic table, but let's talk about sodium. And sodium has a symbol Na, which we've looked at many times there. So basically a sodium atom consists of a nucleus, I'll draw it as one big giant dot, and an electron cloud surrounding it. Now again, remember I told you in the beginning, I said that atoms really aren't like a solar system. I told you that many times. They're not like a solar system, but that picture does have value. It helps us visualize things like ions. So even though we know it's not like a solar system of orbiting electrons, it's really waves. Electrons are waves, and so are the protons, by the way. But it is still useful for us to think about that solar system model, especially in this lesson, even though we know that we're going to revise it later. Now, if we jump over to sodium on the periodic table, it has an atomic number of 11. Remember, this is the number of protons in the nucleus. So because sodium has an atomic number of 11, we can write down right away that, I'll put a little arrow here, right there, pointing to the nucleus, that there's 11 protons. And for protons, you'll put P with a little plus sign there, 11 protons in the nucleus. And there's also some neutrons. I'm going to put neut for neutrons. Now, I'm representing the nucleus as a single dot, but you know that there's individual protons. There's 11 of them, and there's also neutrons. I'm not writing down the number of neutrons for two reasons. First, neutrons have no charge. Ions are all about charge, so the number of neutrons doesn't matter at all. It has no impact. The number of neutrons affects the mass of the atom or the ion, but it doesn't affect the charge. Number two, each sodium atom, remember we can have isotopes, which are different numbers of electrons. One of those will be the most stable, most abundant version, isotope of sodium, but there are going to be other isotopes of sodium in nature. So the actual number of neutrons doesn't really matter for ions, and so I'm not going to write down how many neutrons are there. I can go find out, and I could write it down, but it won't affect anything. All we care about is that there's 11 protons in the nucleus. And because there's 11 protons in the nucleus, then surrounding the nucleus, which I'm kind of encasing as a dotted line here. I'm not saying all the electrons are on the dotted line. I'm saying they form like an electron cloud that's kind of like inside of this dotted line. We know that there has to be 11 electrons. How do we know there has to be 11 electrons? Because if you have a neutral atom of sodium, I haven't made an ion. I'm just talking about a neutral atom of pure sodium. Periodic table tells us it has to have 11 protons, and in order for the atom to be balanced electrically, it has to have an equal number of electrons. So on the periodic table, all of these numbers, these atomic numbers, they're all telling you the number of protons in the nucleus, but they're also telling you the number of electrons surrounding the nucleus for the neutral atom. If you start gaining or losing electrons, things change. But for the neutral, basically, garden variety atom, that's just a neutral atom, the atomic number tells you how many protons are in the nucleus, and it also tells you the number of electrons that must be surrounding the nucleus in the electron cloud or into the orbit, so however you want to visualize it. All right, so because this thing has an equal number of protons to electrons, if you just add them up, the protons have a positive charge and the electrons have a negative charge, and there's 11 of the positives and 11 of the negatives. When you go back to algebra, a positive 11 plus a negative 11 is just 0. So because of this, the overall charge is 0. We say the net charge is 0. So we say this is neutral. And what we mean by neutral, it means the net charge. Yes, we know the protons are positive. Yes, we know the electrons are negative. The net charge is what happens when you add them all together from a distance. When you're looking at something, you're going to look at the algebraic sum of the charges from a distance. It looks like one object with the total charge, which will just be 0. So let's move along and do the same exercise for another atom on the periodic table. Let's just pick chlorine. We could pick anything, so we'll pick chlorine. And we've used it enough to know now that chlorine has a chemical symbol, Cl, right? And so let's draw a little atom of chlorine. Well, it's going to have a nucleus. I'll just draw a little thing. And it's going to have, these are not to scale, okay? I'm not saying this is bigger than this or anything. I'm just drawing little dotted lines here. So we have a nucleus in the center, which consists of what? It has protons in there. How many protons are in a chlorine nucleus? Well, you go over here and you see chlorine has atomic number 17. That means that it must contain 17 protons. So 17 protons. And there's also some neutrons, so I'll write them down, but they don't affect anything, so I'm not going to put the number of neutrons. We could go figure that out if we wanted to. Now, surrounding the nucleus are electrons. How many electrons? Well, for a neutral atom of chlorine, it has to have 17 electrons because it's neutral, right? And the same thing as before, because we have an equal and opposite number of protons and neutrons, then we add them up. Positive 17 plus a negative 17 gives us 0, so this thing is neutral also. So in the beginning, I told you that atoms are neutral, electrically neutral. This is why, because they have an equal number of positive protons in the nucleus as compared to the number of electrons surrounding the nucleus. All atoms on this periodic table have equal and opposite number of protons and electrons. Now, that's what an atom is. Let's transition into making an ion. If I take an electron away from here, then I'm going to have an imbalance. If I take an electron away from here, or if I add an electron to either one of these situations, I'm going to have an imbalance and I will not have a neutral atom anymore. So anytime you have an atom that's not neutral, we have another word for it. We call it an ion. So anytime you see the sodium ion or the rubidium ion or the iodine ion, you know that it's basically just an atom from the periodic table with either some electrons removed or some electrons added. Because you can add or remove electrons from an atom, and anytime you do that, you have an imbalance, a charge imbalance, which makes it what we call an ion. All right, so let's go down and draw a picture. Where do I want to do it? I guess we'll do it right here. Let's go do it right below. Let's do the same thing. So an ion is an atom with a net positive or negative charge. So POS is positive or NEG is negative. And the way you do that is you add or subtract electrons. And let me tell you something nobody told me in the beginning. Why are you talking about removing electrons? Why don't you talk about taking the protons out or adding a proton in there? Basically, you can't do that in chemistry. Okay, what is holding these protons in the center here is, remember, all these protons are positive, but they're all bunched together. All the protons want to repel each other anyway, so why doesn't the nucleus just blow itself apart, right? Because alike charges repel, right? Well, the reason I mentioned it before is because there's another force of nature called the strong nuclear force, which is even stronger than the electrical force, which is millions of times stronger than gravity. So it's inconceivable how strong the strong nuclear force is. But it's able to overcome the repulsion of the protons and hold the nucleus together. But the catch is that the strong nuclear force only acts on extremely small distances. It only acts inside the nucleus. It doesn't reach out like gravity and have a force or a large enough force to be felt by things around it. It only acts inside the nucleus. All right? But basically, in order for you to take a proton and rip it out of there, would require an enormous amount of energy because the strong nuclear force is incredibly strong. It's inconceivably strong. And it's also buried inside the atom, inside all the layers of electrons that are also orbiting on the outside. So there's two reasons you can't really do that. Number one is because the electrons are shielding the nucleus, and if you try to do something to the atom, the electrons are going to come off first, and that's just going to happen first. But even if you took all the electrons away and you just had the nucleus left and you wanted to rip a proton out, you can't do it because the strong nuclear force is too strong. If you were able to split an atom in half or remove a few protons, that would be called nuclear fission, right? If you were to add a proton, that would be called nuclear fusion. Those are nuclear processes, and they release a ton of energy, an incalculable, well, it's not incalculable, but an inconceivable to a human amount of energy. That's the realm of nuclear physics, nuclear chemistry. Regular chemistry is chemical reactions. It deals with electrons. Electrons can be added or subtracted to atoms relatively easily. Dealing with the nucleus is millions of times more energy. So you just aren't doing that in a chemical reaction. So an ion is an atom that has a net, I'm going to underline net, positive or negative charge. There's actually two kinds of ions we're going to learn about. We have what we call a cation, and we have what we call an anion. A cation is an ion with positive charge. And what do you guess this is? An anion is an ion with a negative charge. All right, so we have just different words, right? Because I might reference this element, it might form a cation, or this element might make an anion. And you know immediately, okay, that tells me if it's positive or negative. Anion means it's got an overall net negative charge, and a cation means it has an overall positive charge. How do you make cations and anions? Well, you're either going to add or subtract electrons. That's the only way to do it. You can't mess with the nucleus. It's buried in the center, and it's nuclear. It's the strong nuclear force. You're not going to pull a proton out. You're not going to do it. Not with chemistry. You have to use a nuclear process for that, which is way more energy. So the only way to do it is to add or subtract electrons, which happens all the time. Even sunlight can ionize. We call it ionize an atom. Remove an electron from an atom, for instance. Okay, so let's draw some pictures of what these atoms, these sodium atoms and chlorine atoms, might look like if we were to ionize them. So if we have this situation and we take an electron away from this, then we have what we call a positive sodium ion. The way you write that is Na, and you put a plus sign there, just like we have the protons, P plus and E minus as a superscript. You write it as plus, and this means implied +1. That means it has a charge of +1. How do we do that? Well, what we do is we examine, I guess I'll put ion here. You examine what that would look like. Now, the nucleus for the sodium atom has 11 protons. That's not going to change. So when you go over here, draw that nucleus there, and you have some electron cloud going on around here. How many protons is it going to have? Well, it's going to have the same thing. It's going to have 11 protons, and it's going to have the same number of neutrons, right? Because remember, you're not altering that at all. But what you are doing is you're taking away an electron, right? You're taking away an electron from the cloud out here. So whereas before the neutral atom had equal and opposite, had 11 electrons, if you take one away, you actually only have 10 electrons surrounding this atom. Now we call it an ion. Now what happens when you have the situation with 11 protons in the nucleus and only 10 electrons around this guy? What you have is you have a net charge of +1. Net charge of +1. And the way we write that is we write it as a positive exponent, or typically we write charges as with the sign on the back side of the number. So we can write it as 1 plus. So it's a net charge. When I use the word net, I mean we're adding up the positive and negative. We really have a lot of positive and a lot of negative charges, but we don't care about the actual number. We care about the discrepancy or the difference between them. The deficit between positive and negative is what matters. So the net charge, from a distance, when you're looking at this from 10 miles away, it has 11 positives and 10 negatives, and so overall it looks like a net of a charge of plus 1. So this is what we call a cation, a sodium cation. Okay. Now let's do the same thing with chlorine. So we have chlorine. I guess let me go to black again. Chlorine ion. Right? So we're going to do the same thing. How many protons did chlorine have? 17 protons in its nucleus. So we're going to do the same thing. We'll have a nucleus. We'll have some electron cloud around there. And we had 17 in the nucleus, right? So I'll go ahead and do that. There's 17 protons. And there was also neutrons, which don't really participate. We don't care about it. And in this case, instead of taking an electron away, we're going to add an electron. We're going to add an electron to this cloud. So before, it had 17 protons and 17 electrons. If we add an electron, then we're going to get 18 electrons, right? So if we add, we could of course take we can of course take an electron away from chlorine. I mean, you can do that. You can shine some some high energy light on a chlorine atom, and then you can kick off an electron, and you could remove an electron. But for now, let's just consider the opposite situation. Let's add an electron. So we go up in terms of electrons. From the 17 we had to 18. So what does this mean? The net charge is what? Well, you have 18 negatives and only 17 positives, so it's really 1 minus. Now, it's -1, but we usually rewrite the sign on the other side of the number in terms of charges. So it's 1 minus. So you have a situation where this chlorine ion no longer is neutral. So what we do is we put a minus sign up there to indicate that it's an ion. So we have a sodium ion indicated by the positive sign, and we have a chlorine ion indicated by the negative sign. The positive sign tells me that this entity is no longer neutral. It has a positive charge, and moreover, it has a net positive charge of 1 as an overall net charge on the object. This has an overall net charge on the object of -1. Now let me ask you a question. What's going to happen if you have an object with an overall positive charge of +1 come into contact with another object with an overall negative charge of -1? The numbers don't matter, but if one is positive and one is negative, you know that opposites attract. The Coulomb force of the electric force is millions of times stronger than gravity. Anytime you have opposite charges, it's going to attract. They are going to come together and stay together. They are going to be bonded together, and that's called an ionic bond. And when you have the sodium come into contact with this chlorine, it's going to make sodium chloride, which is table salt. We're going to talk a lot about this later. This is not a lesson in formation of compounds, but this is what's happening. The sodium loses an electron to become positively charged. The chlorine gains an electron to become negatively charged. And then once you have these oppositely charged ions, they come together and they stick, which we call a bond. And we call it an ionic bond. Now you know why it's called an ionic bond. Because the objects formed ions, and then they bonded. Ionic bond. Electron transfer. We said before, ionic bond means electron transfer. Notice that if this chlorine really wants to gain an electron, and this sodium really wants to lose an electron, then what's going to happen is the electron is going to be transferred from here to here. And then once the transfer happens, we have the ions, and then they stick together. And that's called an ionic bond. So the point of this lesson is to illustrate to you that all of these atoms on the periodic table are neutral. The atomic number tells you the number of protons, and for the neutral atom, they have an equal number of electrons surrounding. If you add an electron or subtract an electron to any of these atoms, you form an ion. If the overall charge on the thing is a positive ion, we call it a cation. If the overall charge on the thing is negative, we call it an anion. And then once the anions and the cations are floating around, of course, they're going to be attracted to each other and bond together, which leads to a ton of chemistry that we're going to get into very, very shortly. That's called an ionic bond when the electron gets transferred from one object to another. Now, before we go and solve kind of our first real problem here, I want to talk and refresh your memory of something I mentioned in the lessons on the periodic table. I'm going to refresh your memory through several lessons because we're getting very close to needing to use this information. And so I want you to get it comfortable with it through osmosis, basically, by mentioning it several times. So this periodic table is set up where the noble gases are all in the right-hand column and they are unreactive. We're going to learn why they're unreactive later, but I'll tell you it's just because the electron structure, the way the electrons are filled around those atoms on the right column, is very stable. So because of that, and because chemistry involves electrons being transferred or shared, and because those are stable, those noble gases, you can think of them being like nobility. They don't talk to very many people and they don't react really with anything really. And they have a very stable outermost electron structure. We call it electron configuration. And so the atoms that are right next door here, the halogens here, they're very reactive because they want to look like their nearest neighbor's noble gas electron configuration. Why? Because we're going to learn later that that configuration of electrons is stable. When something is stable, it means it wants to happen in nature. It's like rolling a ball downhill. You're more stable at the bottom of the hill. Things just like to progress in a certain way. Going downhill is one of them. Lower energy, going downhill is a more stable, at the bottom of a depression is a more stable position. So things progress naturally in that way. These electrons that are surrounding these atoms are also more stable. So all the atoms, they want to get to a more stable configuration, which is basically a lower energy state down here. We'll talk about the energy part of it later, but it tries to get to be more stable. That means chlorine really wants to accept one more electron to have the same number of electrons as argon. Remember, argon has 18 electrons, chlorine has 17. If it could gain one more, it would be more stable. Why would it be more stable? We're going to talk about it later, but it has to do with the electric force pulling an electron in very readily to chlorine. It wants to take one electron. Fluorine wants to take one more electron to look like neon. Bromine wants to take one more electron. Now oxygen is 2 spots over from its nearest noble gas. It wants to gain 2 electrons. Sulfur wants to gain 2 electrons, and so on. So the elements over here, you can tell how many electrons they want to gain because of the column they are in, the group that they are in. And so you can predict very readily what these want to do. They want to become negative ions, is what I'm trying to say. When you gain an extra electron, the chlorine gains an extra electron, it becomes an anion, which is a negative ion. It wants to be like this. It wants to gain that extra electron to look like its nearest its nearest noble gas neighbor, which in that case is argon. Now that's what's happening over here. On this side of the table, sodium, it doesn't want to gain an electron, because if it gains electrons to be close to its nearest neighbor noble gas, it would have to gain 1, 2, 3, 4, 5, 6, 7. It would have to gain 7 additional electrons. Number one, where's it going to get them from? And number two, that is going to require more energy to pull those extra electrons in. It's going to be much, much more energetically favorable for sodium to just lose its outermost electron, because it has 11 of them. When it loses its outermost electron, it will have the same outermost electron configuration as neon, which is another noble gas, which is also stable. So everything in this column wants to lose an electron. Potassium loses an electron to look like argon. Rubidium loses an electron to look like krypton, and so on. All right. Now these right next door, they don't want to lose 1 electron. Calcium has to lose 1 and then 2 electrons to have the outermost configuration of argon. So the big picture is that you can always predict how many electrons it wants to gain and lose, but by just looking at the group number. We want to lose 1 electron here, we want to lose 2 electrons here, we want to gain 1 electron here, we want to gain 2 electrons here. It's bulletproof and very easy to use that to predict for these elements. For the elements that get farther away from the edges of the table, like cobalt or iron, they can do multiple different things. It's not so readily apparent what it will do as far as how many electrons it'll gain and lose, but the elements in the main group elements, these here and these here, are oftentimes very predictable. And we use the periodic table to do that. So we're going to mention that again and again, because knowing the ions, knowing how many electrons it wants to gain and lose, will tell us what ion it wants to form. Once we know what ion wants to form, we know how they're going to combine together. And we'll get into that a little more later. All right, so let's solve problem number 1. Let me go to a blank board here. And this is not going to take very long. Problem number 1 is not going to take very long. Let me go down below here, I suppose. And what I'm going to do is I'm going to write down an ion, and we're going to answer the question, how many protons and electrons do these have? So here we have nickel. The nickel atom, which is an ion with a positive charge. Notice we wrote the charge as 2 plus. We didn't write it as positive 2. It's convention. We write it as 2 with a plus sign after it. All right, so that's just something you're going to have to remember. So how many protons, how many electrons? So we know it's nickel. So we can go over here to nickel on the table, and we see nickel is right here with atomic number 28. 28 means there's always 28 protons in the nucleus. So we'll write down 28 protons in the nucleus. I write proton as P with a plus sign. And that comes straight from the periodic table. Now, if this were a neutral nickel atom, then it would have to have 28 electrons. It would have to have 28 electrons to balance it, but this has a positive 2 charge. So we must have lost some electrons overall to do this. So if the neutral atom has 28 protons and 28 electrons, this one must have 26 electrons because of this. And the way that because it has a positive 2 overall charge. And you can figure that out because if it was 28 and 28, then it would be balanced. But by losing 2 electrons, we have an overall charge of positive 2. Just add them. 28 positives plus, or subtract, or however you want to think about it, but plus a negative 26 is an overall charge of positive 2. All right, next, we want to take a look at the ion sulfur with a negative 2 charge, which I've already, I did it right. Thought I did it wrong, but I did it right. So again, we write the number with the sign after it. How many protons and electrons are in this ion? And by the way, is this an anion or a cation? This is a positive charge, so it is a cation with the positive charge. And this one, is it a cation or an anion? This is an anion because it has a negative charge. So sulfur, how many protons are in the nucleus? Sulfur has 16 protons in the nucleus. So just write down 16 positive protons in the nucleus. Now the neutral sodium atom would also have 16 electrons, but this one isn't neutral. It's got an overall charge of negative 2 or 2 negative. So it has to have 18 electrons altogether, 2 more than the balanced number, which would be 16. So 18 protons, 16 protons, 18 electrons. All right, 2 more of these. Let's take a look at bromine, and this is just a negative 1 charge. Negative 1 charge, so we don't have to write the number 1 here. So where is bromine on the periodic table? Bromine is over here, and it has 35 protons in the nucleus. So this thing has 35 protons in the nucleus, and we know it has an overall negative charge. The neutral bromine atom should have 35 electrons, but we have to have 1 additional because it has an overall charge of negative 1. So this has 36 electrons surrounding that nucleus. All right, and then finally, D, we have chromium 3 plus, which has an overall charge of positive 3 there. All right, so chromium on the periodic table, when we go and take a look at chromium, where is chromium? Chromium. Right here, chromium. And so the atomic number of chromium is 24. That means there's 24 protons in the nucleus. Now the balanced neutral form of chromium atom would have 24 electrons, but we have to have less than that. We have to have 21 electrons. Because balance would be 24, we have to have 3 less than that in order to give me an overall charge of positive 3. The imbalance is in terms of positive 3. Now let me just take a second. We just talked about what these atoms like to do on the periodic table. And I'm giving you a little practice with this as we go because we're going to use it very soon. So let's take a look at the first one. We said, let's take a look at silver. An overall charge of, this is not silver, I'm sorry, sulfur, negative 2. Sulfur is right here on the periodic table. We are saying that it likes to attain a stable configuration of the closest noble gas, argon. It wants to gain 2 electrons in order to have the same number of electrons as argon. Gain 2 electrons. And so sulfur does indeed like to have a charge of negative 2 and to gain 2 electrons from its neutral counterpart. What about bromine? Bromine is over here in the periodic table, and so it is trying to attain the electron configuration of krypton. It's going to try to gain 1 electron to do that, and so bromine wants to gain 1 electron. 35 would be neutral, gaining 1 electron would be 36 there. Now nickel and chromium are a little different because nickel and chromium are here in the center of the table. Nickel is right here and chromium is right here. And it's difficult to predict what these atoms want to do in the center as far as how many electrons are going to be gained and lost. There's some rules of thumb, and overall you're going to learn that there's only usually a couple of different ways in which they like to behave, and we're gonna learn about how to handle that later. Those are the transition metals. They can do, in other words, they are a little unpredictable and they can do multiple different things. For now, we're going to put that aside and we're focusing on the edges of the table, the most reactive elements here, the most reactive elements here. Gaining or losing, that's very highly predictable. All right, now what we're going to do to wrap up this lesson is I'm going to write a table down on the board and we're going to fill it in. And so we're going to have symbol, right? Symbol. Then we're going to have protons. Then we're going to have neutrons. Then we're going to have electrons. Then we're going to have net charge. All right, so here we have this, 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 and this. And what we're going to do is I'm going to fill this table out. I'm going to give some information into it, and then we're going to fill out the rest. So for the first thing I'm giving you, it's cobalt, 3+, and the mass number you can still write up here, 59. Remember, we were writing those mass numbers before. And then I'm going to draw a line, so we're going to fill in all this information right here. And then also, I'm going to fill in 34, and then 46, and then 36. All right, so this is what I'm giving you. What I want to do is fill in all of these spots and then all of these spots in the second line here. So we have to think through it. First of all, let's take a look at this. This is cobalt, and you can see right away that it has a charge of +3. So the net charge, this is an ion. We'll also just provide the mass number, that's fine. This is the ion, it has an overall charge of +3. So the net charge is going to be written as 3 positive, right? And you can just write that straight away by looking at the symbol. Now it's cobalt, so let's go look at the periodic table. Where is cobalt on the periodic table? It's right here, atomic number 27. So no matter what, we know that the number of protons in the nucleus of this thing has got to be 27. So we can easily do this, right? And then we can also fill in the electrons, right? Why? Because the neutral form of cobalt would also have 27 electrons, but this one actually has a charge of +3. So we have to have fewer electrons by 3, right? So we know that there has to only be 24 electrons because there has to be an imbalance. We have to have more protons than electrons by 3. So we write this down and then we know we have to have 3 less electrons. Finally, how many neutrons do we have? We're given the mass number. The mass number is protons plus neutrons. And so the number of neutrons must be 32 because the protons plus the neutrons have to equal this. So you have 50 and then you have 9. And so we filled out the first kind of leg of that table there. All right, let's go over here and take a look at the second part of the problem. We have 3 numbers filled out. What is the net charge? That's the easiest thing. The number of protons is 34. The number of electrons is 36. We have more electrons by 2. So the charge has got to be -2. All right, and now we have enough to write down what we have here. The number of protons gives us the symbol. So we go look at atomic number 34. 34 is selenium, Se. So we know it has to be Se. We know the charge on this thing has to be a -2, so we write that as 2 negative. And then we have to write the mass number up here, which is the protons plus the neutrons, which were given to us. So you have 70, and then the 4 and the 6 make 10 more, so it's 80. So 80 goes right here. And that's it. That problem is concluded. All right, so in this lesson, we've covered a tremendous amount of material. Basically, all these elements in the periodic table, they're all balanced because they have balance in terms of charge because they have equal number of protons and electrons. But what happens is these atoms, they're either going to gain or lose electrons depending on what the electric force is going to do to it. We're going to learn that the position on the table tells us if it's going to gain or lose electrons. We've already talked about that. And they're always trying to attain a noble gas outermost electron configuration. And we're going to talk about the details why they're trying to do that later. It all comes down to the electric force, but it allows you to predict how many electrons it's going to gain or lose, which tells you what ion it's going to form and the charge on the ion that it will form. Once you have and know what ions are formed, then you can predict what chemical compounds will form, because when you have negative and positive ions, they're going to be attracted together. And we're going to talk about how to write down the chemical formula for the product of what has. So we're building ourselves into chemical reactions, learning about ions first, knowing that it's an imbalance between the protons and the electrons and so on. So I'd like you to practice this, make sure you're getting all these correct, and follow me on to part 2. We'll wrap up the concept of ions in chemistry. Learn anything at mathandscience.com.